Okay, we'll look at some of the questions and the exercises that will be similar to the ones that will be on your third exam, which will be on Tuesday, November 1st, and it will cover chapters 5 and 6. Also, you will have a help sheet that will assist you with some of the problems on the exam. We'll start with the 6 questions that will be on your exam. Question number 1 is, what are the requirements for a probability distribution? Here there are only 2 requirements. One of them is that the sum of the probabilities must equal 1. And second, each probability value must be between 0 and 1. And then number 2, what are the requirements for a binomial probability distribution? In this case here, the procedure must have a fixed number of trials. By the way, there are 4 requirements. That's the first one. Must have a fixed number of trials. Second, the trials must be independent. Then for each trial, all the outcomes must be classified into 2 categories. And then for all the trials, the probability of success must remain the same. So those are the 4 requirements of a binomial probability distribution. The procedure must have a fixed number of trials. The trials must be independent. And for each trial, the outcomes must be classified into 2 categories. And for all the trials, the probability of success must remain the same or remain constant. Question 3, what are the properties of a standard normal distribution? There are only 3 properties that you need to know. One is that the graph is a bell-shaped curve. Second, the mean is equal to 0. And then the standard deviation is equal to 1. So those are your properties, 3 properties of a standard normal distribution. A bell-shaped curve for the graph, the mean is equal to 0, standard deviation is equal to 1. Number 4, what is the purpose of a critical value? Here, the critical value, as defined in chapter 6, I believe, is that z-score on the borderline that separates the z-scores that are likely to occur from those that are unlikely to occur. So the z-score is what separates the z-scores that are, well, the critical value, it separates the z-scores that are likely to occur from those that are unlikely to occur. That's the purpose of a critical value. Question 5. What are the 3 statistics? Well, 3 statistics are unbiased estimators. One is the mean, the second is the variance, and the third is the proportion. These 3 target the population parameters. Each of those population parameters, the mean, the variance, and the proportion, are your 3 statistics that are considered to be unbiased estimators. And question 6, what does the central limit theorem say about a population with any distribution? Well, it says for a population with any distribution, whether it's normal or not, the distribution of sample means approaches a normal distribution as your sample size increases. So as the sample size increase, the sample means, or the distribution of the sample means, will approach a normal distribution. That's basically what the central limit theorem is saying. Okay, so those 6 questions will be on your exam. The rest will be just simple exercises that we've been doing on the homework and also as examples in class. Okay, the first question, you're to, in fact, with all the questions, you're to show your work on these, if at all possible. And also, the ones that are in bold print are the ones that you may use only your graphing calculator to do those. All right, in question number 1, you want to determine whether the random variable is discrete or continuous. Okay, discrete is countable, whereas continuous is measurable. So in part A, the time it takes for a light bulb to burn out, that time is measurable. That means it is continuous. And part B, the number of statistics students now reading a book, we can count the number of statistics students that are reading a book. So that would be considered discrete. Okay. So know the difference between a discrete random variable and a continuous random variable. That's discussed in chapter 5 in your text. Okay, question 2, or exercise number 2. Suppose a baseball player had 243 hits in a season. In a given probability distribution, the random variable x represents the number of hits the player obtained in a game. And here's the table that's given to you. You can refer to that on your review sheet. And in this problem number 2, you have 2 parts. You want to compute the mean of the random variable x, and B, compute the standard deviation of the random variable x. All right, in this case here, what I've done is created a table in vertical form for the x and p of x. Now, the next column is x times p of x. What I'm going to do here is multiply the x value times its respective probability. So like 0 times 0.0918, that's simply be 0. For 1 times 0.4997, that'll simply be 0.4997. And then 0.2512 times 2 will be 0.5024. And then 3 times 0.1035 will be 0.3105. And then 4 times 0.0338 will be 0.1352. And then 5 times 0.0200 will be 0.1. Now, it's this column that's going to help me answer part A, because in this case, if you recall the formula for finding the mean in a probability distribution, that's going to be the sum of x times p of x. So what I'm going to do here is add these numbers in the x times p of x column. That will give me the sum. That will give me the answer of part A. So 0.4997 plus 0.5024 plus 0.3105 plus 0.1352 plus 0.1 would be 1.5478. And I will ask you to round to 2 decimal places, so this will be 1.55 for the mean. Now the B part, they want sigma, which is your standard deviation of that random variable x. So we need to finish this table right here. Okay, so here, the x squared, I'm going to square the x's in this column here. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And this is actually 4. Okay, now I'm going to take this column and multiply each one of those x squares by each one of these probabilities here. So 0.0918 times 0 is 0. 0.4997 times 1 is 0.4997. And 0.2512 times 4, that would be 1.0048. Then 0.1035 times 9 would be 0.9315. And then 0.0338 times 16 will be 0.5408. And then 0.0200 times 25 will be 0.5. Now I'm going to add this up, because part of the formula for finding the standard deviation is going to be this. But here's the entire formula. The summation of x squared times the probability of x minus mu squared. So if I add this up, this sum will give me this part right here. Okay, so here 0.4997 plus 1.0048 plus 0.9315 plus 0.5408 plus 0.5 will be 3.4768. This part is the answer for this, is part of the summation of x squared times p of x. So here I'm going to have the square root of that 3.4768 will be put in place of this expression right here. Minus mu, which is, and I'm going to use the 1.5478, and that's going to be squared. And all of this can be put in the calculator. So if I have, say, second x squared, 3.4768 minus 1.5478, and then hit the x squared button, and then close the parentheses, I will get 1.039 to, let's say, 2 decimal places, 1.04. So the standard deviation here will be 1.04. Okay, so that's my answer for part B, finding the standard deviation as 1.04. In part A, the mean was 1.55. And you'll be told to round to a certain number of decimal places, in this case, 2 decimal places. Question number 3. Now notice in question number 3, that's printed in bold. That means you're allowed to use the calculator for this one. I'll show you how to use that. Assume the procedure yields a binomial distribution with a trial repeated n times. Use your calculator to find the probability of x successes given the probability p of success on a given trial. And here in part A, you got n is equal to 2, x is equal to 1, and p is equal to 0.80. So here we use the binomial probability density function on your calculator. And the way you'll enter that, you'll enter n first, then p, which is your probability, and then x is the successes that you're trying to find. So with part A, this is how we'll set this up. BION, the binomial PDF, and then n is 2, your p is 0.80, and x is 1. Okay, and here's how we enter that on the calculator. We always go to second and then vars to get to the distribution menu, second and vars. We want to use our down arrow key to find binomial PDF, which is this selection right here. And then press enter. And then we're going to enter n, which is the 2, and then comma. Your p was 0.80, and then comma, and your x, which is 1. That's the order you will enter this in. And it's quite easy because if you know the alphabet, n comes before p, p comes before x, so that makes sense. And then press enter. And here you'll get 0.32. And we're going to round this off to 4 decimal places because probability is usually going to be in 4 decimal places. So this will be 0.3200. And part B is done the same way. You're still going to use the binomial PDF. N is 7, your P is 0.85, and X is 5. Okay, so using a calculator, we press second and vars. Use our down arrow key to find binomial PDF. And then press enter. And then enter the n, which is 7, comma, 0.85, comma, 5. Close the parentheses, and then hit enter. And we're going to round to 4 decimal places. So here this will be 0.2097. Okay. And by the way, you have to write like this. The probability that you have 5 successes will be 0.2097. And the other one, in part A, the probability of exactly 1 success, that would be 0.3200. That's how you'll write those. Okay. Okay. Number 4 is another problem that's in bold print. Here you can use the graphing calculator. A brand name has a 50% recognition rate. If the owner of a brand wants to verify that the rate beginning with a small sample of 10 randomly selected customers, find the probability that exactly 5 of the 10 customers recognize the brand name. Also find the probability that the number of customers who recognize the brand is not 5. All right, let's take a look at what we know. Here, the brand name has a 50% recognition rate, so that's your P, which will be 0.50. 50%, that's a decimal, that's 0.50. We know we have a small sample of 10 randomly selected customers, so here, N is 10. And we're trying to find the probability of exactly 5 of those 10, so that's your X, which is 5. And in this case, we can use the binomial probability density function on our calculator. And here N is 10, your P is 0.50, and X is 5. So using the calculator, we go to second and vars for the distribution menu, and we hit our down arrow key to go to binomial PDF, and then press enter. We enter N, which is 10, then comma, the probability, which is 0.50, comma, and then X, which is 5, and then press your right parentheses, and then hit enter. In this case, we round this up to 4 decimal places, so it'll be 0.2461. So the probability of exactly 5 successes will be 0.2461. Now the other part is finding the probability that the number of customers who recognize the brand is not 5. So the probability where X is not equal to 5. Well, that's simple, because we know the probability of X is equal to 5. The probability of X is not equal to 5 would just be the complement, or 1 minus that probability. So it'll be 1 minus 0.2461, which will give you 0.7539. Okay. So the probability of exactly 5 people recognizing the brand name will be 0.2461. That means that there is a 24.61% chance or probability that exactly 5 of those customers recognize the brand name. And here there's a 75% chance that not 5 of them know what the brand name was. Because it could be more than 5 or less than 5. Question number 5. Assume that the procedure yields a binomial distribution with n trials and the probability of successes for one trial is p. Use the given values of n and p to find the mean and the standard deviation. Also use the range rule of thumb to find the minimum usual value, mu minus 2 sigma, and the maximum value, mu plus 2 sigma. And we're given n is 175 and p is 0.4. Well, it is a binomial distribution with n and p given, so the mu, which is the mean, is n, times P. So we're finding the mean, which is your mu, that's N times P. We just simply take 175, which is N, multiply that by P, which is 0.4. So 175 times 0.4 will give you 70. So the mean, which is our mu, is 70. And sigma, which is your standard deviation, is the square root of N times P times Q. Well, we know N is 175 and we know P is 0.4. Q is simply 1 minus P, or 1 minus 0.4, which will give you 0.6. So Q will be 0.6. So we'll just replace N, P, and Q in this particular formula. N is 175 times P, which is 0.4, times Q, which is 0.6. And we can type all this underneath in the calculator. I'll show you how that's done. Press second, x squared, then do 175 times 0.4 times 0.6, and close the parentheses. And then hit enter, and you'll get to two decimal places, let's say 6.48. So the standard deviation here is 6.48. Now in this case here, we want to find also the minimum and the maximum usual values here. So in this case here, let's find the minimum, which is of course mu minus 2 times sigma. And in this case, mu was 70 minus 2 times sigma, which is 6.48. That would be 57.04. Okay, I just did that on the calculator. Now for the maximum, you'll have mu plus 2 times sigma. So 70 plus 2 times 6.48. That'd be 82.96. So the minimum usual value will be 57.04. The maximum will be 82.96. So here we're just using the range rule of thumb to find the minimum and the maximum usual value. So values between 57.04 and 82.96 are usual. Anything outside that would be unusual. Okay, question 6 deals with a normal distribution. Now this one we'll have to work out here. Assume that the thermometer readings are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 Celsius. You want to draw a sketch and find the probability that a randomly selected thermometer will have a reading less than 0.24. Now this one you'll have to use your table 8-2 in order to do this particular problem. So in this case here, let's go ahead and draw the normal curve. So here mu is 0 and sigma is 1.00. And we have a thermometer of 0.24, a thermometer reading of 0.24. Let's say 0.24 is to the right of 0. And we're looking for this area to the left. That's what we want, the area to the left of point 24. Okay, now it's already in a standardized z-score because mu is 0 and sigma is 1.00. So here we can just go directly to table A-2 and find point 24. So here's point 2 for the first part, and then the hundredths place is your 0.04. We read down and we find 0.5948. That represents the area to the left of point 24, which is that shaded area, 0.5948. So here, the probability of getting a thermometer reading less than 0.24 will be 0.5948. And that's all there is to it. All right, question 7. This one we get to use the calculator because it is printed in bold. Find the critical value for z is, well, z sub 0.05. Now that subscript of 0.05 represents the area to the right-hand side. So here the critical value is what we're trying to find. And this shaded area is 0.05. Now here we can use the calculator, and the one we're going to have to use is inverse norm. And now, if we're going to use the inverse norm, we need to know what the area is from on the left-hand side. So if this is 0.05, the area to the left of that will have to be 0.95, because the area underneath the curve is 1. So if we know this is to the right of that is 0.05, then the area to the left would be 0.95. And that's the only thing we have to enter in the calculator. So to get the inverse norm, we press second and vars. And then we select number 3 for inverse norm. And then type in 0.95, close the parentheses, and then hit enter. Now this one, to 3 decimal places, this will be 1.645. Because that's the most common number that we're going to be using in chapters 7 and 8. Okay, so that critical z value, or that critical value that we're looking for, is 1.645. Okay, number 8 is also another calculator problem that we can use the graphing calculator to work out. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 20. And here you want to find the probability that a randomly selected adult has an IQ between 84 and 116. So here's what the normal curve will look like. And here the mean is 100. So here, this is where mu is. That's 100. And we know our standard deviation is 20. Okay, 84 is to the left of 100. So we're going to mark off 84 right here. 116 is to the right of 100. So here's 116 here. We want this shaded area in between those two. Okay. Now to do this particular problem, we have to use the normal CDF function. The normal CDF function. Okay, and I'll show you how that's done. Again, we press second and vars. We select number 2 for the normal CDF. Now, the low limit, in this case, and I'm going to go back to this one, the low number is 84. The upper limit is 116. And then mu is 100, and your standard deviation is 20. That's how we enter this in the calculator for the normal CDF. The lower limit, then your upper limit, then mu, and then sigma. So here, we're going to enter, after you press second vars and then you select number 2, we're going to enter the first number, which is 84, comma, then 116, comma, 100, comma, 20, close parentheses. And then hit enter, and that will give you 0.5763. And we're rounding this off to 4 decimal places. So here the probability of selecting an adult that has an IQ between 84 and 116. And that's going to be this number right here. Okay, so you have to know the format for the normal CDF. It's always a low limit, then your upper limit, then mu, then standard deviation, or sigma. Question number 9. The length of pregnancies are normally distributed with a mean of 265 days and a standard deviation of 15 days. Here you want to find the probability of a pregnancy lasting 305 days or longer. That's part A. Part B, if the length of pregnancy is in the lowest 4%, then the baby is premature. You want to find the length that separates the premature babies from those who are not premature. Okay, so let's do part A, finding the probability that the pregnancy lasts 305 days long. We always start by sketching the normal curve. And here mu is 265, and sigma, that's your standard deviation, that's 15. So here we want to find the probability that the pregnancy lasts 305 days. So let's mark off 305, which is right here, or longer. So the area to the right is what we're concerned. Okay, now we first have to convert this into a standardized z-score, okay, because it's not 0 and 1 for the mean and the standard deviation respectively, so we need to convert that to a standard deviation using this formula. To a z-score. We use this formula. Z is equal to x minus mu divided by sigma. Okay, and the x that we're dealing with is 305 minus mu, which is the mean, that's 265, divided by sigma, that's 15. So if you do 305 minus 265, which will be 40, divided by 15, that'll give you, to 2 decimal places, 2.67. So the z-score that we're dealing with is 2.67. Then we go to our table A-2 to find 2.67. Here's my table A2. We'll find 2.6, which is on the left side, and 0.07 is up here. So if we read down and find 2.67, you'll see 0.9962. 0.9962. That's the area. Keep in mind that 0.9962 represents the area to the left. You want the area to the right. So we're going to have to do 1 minus 0.9962, which will give you 0.0038. That represents the probability of getting a pregnancy 305 days or longer. So that's the answer to part A, 0.0038. Because you have to keep in mind that the 0.9962 represents the cumulative area to the left. You want the area to the right. So you always do 1 minus that probability. Now, part B. If the length of pregnancy is in the lowest 4%, then the baby is premature. So if you draw a normal curve, on the left-hand side, that shaded area, that's the lowest 4%. Or as a decimal, 0.0400. That's 4%. Now we want to find the length that separates the premature babies from those who are not premature. So here, we're trying to find out what x is. Okay, so here we're finding the x value. You're given the area, so we're going to work backwards here. In this case, we're going to go to the table and find a four decimal value that's closest to 0.0400. Okay, so let's go here and find something that's close to 0.400. And if you look right here, here it is, 0.0401. That's closest to 0.0400. Then we look to the left and look up above. To the left is negative 1.7. And then above it is 0.05. So we'll use negative 1.75 as our z value. So in this case, the z value is negative 1.75. Now to find x, we have to use this formula. X is equal to mu plus, x is equal to mu plus z times sigma. Okay? X is equal to mu times sigma, mu plus sigma times z. And we know mu, in this case, is 265. Z we found out to be negative 1.75, and sigma was 15. So if we do 265 times negative 1.75 times 15, that'll give you 238.75. And 238.75, we're going to round it out to 239. So our x in this case is 239. So those babies that are born less than 239 days, which represents the lowest 4%, then that means that baby was born premature. Okay. And finally, question 10. Assume that women's heights are normally distributed with a mean given by mu, which is 63.7 inches, and the standard deviation given by sigma is equal to 1.9 inches. And there are 3 parts. If one woman was randomly selected, find the probability that her height is between 63.3 inches and 64.3 inches. And then part B, if 10 women are randomly selected, find the probability that their mean height is between 63.3 inches and 64.3 inches. And part C, why can't the central limit theorem be used in part B even though the sample size does not exceed 30? Let's start with part A. We know n is equal to 1 because we're only dealing with one woman. Let's draw the normal curve. We know mu is 63.7 and sigma is 1.9. And in this case, we want to go between 63.3 inches. See, that's 63.3, that's to the left. And 64.3 is to the right. And that's this shaded area right here. Okay? Now here we're going to use the calculator because it is in bold print. And it's best to use the normal CDF menu. Okay? The lower limit is 63.3. The upper limit is 64.3. Mu was 63.7. And your sigma is 1.9. Okay? Lower limit, then upper limit, then mu, and then standard deviation. That's how you'll enter that in the calculator for the normal CDF. So in this case here, we'll select second, and then vars, and then select number 2, and then enter the lower limit, which is 63.3, comma, then your upper limit, which is 64.3, then comma, the mean, which is 63.7, standard deviation 1.9, then close the parentheses, and then hit enter. So here this is 0.2073. So that means that the probability of selecting a woman whose height is between 63.3 and 64.3, that'd be 0.2073. Okay, so that's how you'll write that. All right, now part B, we have 10 randomly selected women. And we want to find the probability that their mean height is between 63.3 inches and 64.3 inches. First things first, n is 10. We got to use this, sigma of x, which is going to be sigma divided by the square root of n, because that's the standard error of the mean. So sigma was given to us as 1.9, and n is 10, so we do square root of 10. So 1.9 divided by the square root of 10 is going to be 0.600833. And I'm rounding this off to 6 decimal places. I'm trying to use as many decimal places as I can in order to come up with an accurate answer. Now, we still can use the normal CDF function, but instead of 1.9, now the lower limit is still 63.3. The upper limit is still 64.3. Mu is still 63.7. However, instead of 1.9 as our standard deviation, we have to use 0.600833. Okay. So second, and then vars, then select number 2. So here we enter 63.3, comma, 64.3, comma, 63.7, comma. Now here we enter 0.600833. Close parentheses. And then hit enter. And this will be 0.5882, rounded to 4 decimal places. So here the probability that the average height of 10 randomly selected women are between 63.3 inches and 64.3 inches will be 0.5882. So that's part B right there. because you have to do sigma divided by the square root of n first to get your sigma of the standard deviation of your sample means, and then use that normal CDF. The lower limit, the upper limit, and the mean are going to stay the same, but it's this last number that's going to be different. Okay. Now they ask in part C, why can the central limit theorem be used in part B even though the sample size does not exceed 30? Well, the reason for that is this. In the problem, we're told that our heights of women are normally distributed. So that tells us that we can use the central limit theorem. Even though the sample size does not exceed 30, as long as we have a normal distribution, or if our heights are normally distributed, then that means we can use the central limit theorem. Okay? So that should be enough to assist you with the questions that will be on your exam number 3. And you can view this video as many times as you need to. And also feel free to come by my office to ask any particular questions if you have any. Okay? I'll see you in class on Tuesday.